so the recipient of the Seibel Scholarship, and so the CMU Presidential Fellowship. So so welcome, and so thanks for coming to give the talk. You can give a talk about a tale of evidence and explanations. So great. So I'll give the floor to you.
Yeah, thanks, Jeff, for the introduction, and thanks for having me. I'm very excited to be here. So before I begin, let me say that I want the talk to be interactive. So if you have questions, please feel free to stop, ask, and don't hesitate. So today I'm going to talk about explanations and evidence for deep learning. And this is joint work with a lot of people, Bhuvan, Livio, Mike, William from Google, and my advisors at CMU, Graham and Zach. So let's maybe start first with why we care about interpretability. And let me begin with an example. So in about 90s, when there was a shortage of beds in some hospitals, people were trying to model the probability of death for patients who were coming in with pneumonia. And they were doing so because they only wanted to admit high risk patients, and low risk patients could be treated as outpatients. And they had past data about people in the past who had passed away with pneumonia and so on. So using past data, they were trying to model the probability of death. And if the probability was beyond a certain threshold, they would say that, okay, this is high risk. And even back in the day, they found that neural networks were more accurate than simpler models like logistic regression. And however, when they were trying to analyze some of the data set, what someone suggested that let's train a rule-based classifier and let's try to interpret the rules learned by that rule-based classifier. And one of the rules that was learned and one of the correlations which was later discovered was that people who were coming in with asthma were marked as lower risk. And any medical practitioner would tell you that this seems wrong. So if people have asthma, generally that means they're at a much higher risk. So this is very confusing. Why would it so happen that the model or the data would suggest that people coming in with asthma have lower risk? So anyone in the audience maybe want to guess why that might be the reason?
So maybe they were treated very efficiently because they had asthma.
Yeah, exactly. So this is the reason. They were treated intensively because they were already identified to be people who were already in risk. So because they were treated intensively, they died less. So if you are modeling the probability of death, you would identify that having asthma is actually correlated to dying less, which might suggest that having asthma is lower risk, but it's actually the opposite. So in fact, this is something that was completely missed. And had this model been actually deployed, it would have been disastrous. So we basically need to be more certain about the models we deploy to be sure that there aren't such phenomena that actually happen in real world. There are a lot more reasons to actually work on interpretability. Some reasons could be legal reasons. A lot of countries, for instance, necessitate a right to explanation. So if a model is making a decision that affects you in some way, you have a right to explanation. Also, a lot of models deployed might perform poorly in the wild because the distributions you see during training are very different from distributions that you might encounter in the wild. And there are a lot of other reasons, like maybe closer to our heart might be debugging these models. People are happier with explanations. So if we can show explanations, studies have shown that people are more willing to adopt these models and so on. So hopefully I have convinced you that we want to have models that could provide explanations or are interpretable. Broadly, the community has focused on these two themes. The first one being, what has the model learned? So for instance, if we have a machine translation system that's actually doing English to French translation, people have probed and asked questions like, does this model understand syntax? Does this model know that the source sentence is in past tense, for example? Or does this model understand how many tokens it has consumed, or how many tokens it needs to output more, and so on? So these are, on a global model level, what are traits that the model learns, and are they good traits, and so on. So the first theme is about what's the model doing. And the second theme, which is also the focus of this talk, is that can we explain particular predictions for a given example? And there is a lot of interest in the community. There are lots and lots of papers, analysis, and attribution methods which suggest that, okay, this is the reason why a particular prediction was made. And in general, people have a lot of methods to explain predictions. Very recently, a new track on interpretability and analysis was introduced only this year, and it received over 100 submissions this ACL, 150 submissions this EMNLP, and it was one of the most viewed tracks. While there is a lot of interest, we also face a lot of challenges. One of the key challenges being that we still haven't nailed the terminology. The terminology is loaded, diverse, and sometimes even divergent. And many papers fail to articulate what is the goal of explanation, or rather, what is the specific question to which the answer is an explanation. And clearly, failing to articulate this goal is also failing to evaluate. And I'll specifically focus on evaluation for the first part of the talk. So, how are explanations currently evaluated? A lot of explanations are evaluated by looking closely. So people might look at, okay, so the prediction was numeric and the words highlighted were how many. So a lot of these ad hoc visual inspection is to primarily affirm with our own views that, okay, this makes sense. And this is only a qualitative protocol to evaluate explanations. And a lot of papers typically would cherry pick some examples and suggest that their method actually does what feels like the right thing to do. And this is another example where they were trying to detect atheism versus Christianity in a news group, and there are some highlights and so on. The other methods people have suggested to evaluate is, there was this very recent benchmark called Eraser benchmark, which suggests these two protocols. One is how comprehensive your explanation is and how sufficient your explanation is. So you can measure how sufficient your explanation is by just using the highlighted portion as per the explanation. And if you still are able to drive a lot of accuracy, then that means what you have is sufficient. And the comprehensiveness is, let's say you delete the part of the explanation, and now whatever remains is fed to the model. And if you see a huge drop in your accuracy, that might suggest that whatever you have is comprehensive enough, and there is nothing left that can drive accuracy. So this seems like a reasonable thing to do, but this makes a huge mistake in the sense that it violates one of the key principles of machine learning, which is the IID assumption. A lot of the models were originally trained on full sentences, full paragraphs, but now are being evaluated on these small subsets, which are highlighted by certain explanation techniques. So it is not immediately clear if the performance changes that are observed by these methods are driven because now you have an altogether new distribution, or because they're actually informative about the explanations.
I have a question.
Yeah.
Yeah. So Yeah, I do agree, like highlighting part and then basically ge like getting rid of explanation, those words, or just giving that word. But like as you said, like those words can be like the whole sentence doesn't have any meaning, or they are totally random as such when you give this. Rather than, a good idea wouldn't be like if we have like paraphrases of the same thing with the same semantic meaning, and then we say, if I have the same question asked or something around the same thing, how things are, how how does the model react? Won't that be a better choice rather than like
Yeah, yeah.
basically?
So definitely, I completely agree. A lot of this evaluation and a lot of even explanation generation methods rely on input that is not even a part of the training distribution. As
Hmm.
Vivek just pointed out, that many of these picked out words are not even well-formed sentences. And a better thing might be to actually sample points that are within the distribution and make sense, and whose output you can trust better. But
Hmm.
we still do not have reliable protocols that can do that or have specifically looked at evaluation of explanations.
Okay.
Yeah. And having said that, there are a lot of explanation techniques which have been designed that do not agree with each other. So this heat map suggests and tells us how much overlap we see between different techniques. And what I've done here is I've picked out top 10% tokens selected by different explanation techniques. And I've tried to capture the overlap between the two techniques. And as you can see, the overlap is really, really low. So this graph is a lot red than it should be. And the maximum overlap that I see between two techniques is only 30%, which is remarkably low. So these explanations differ a lot, and yet most papers claim that these are the right explanations based on evaluation techniques that are not very rigorous. Okay, so before actually we even begin talking about evaluation, we need to talk a little bit what constitutes as a good explanation or what constitutes as a good interpretation. So the terminology that we adopt in our work is that explanation or an interpretation of a model's prediction is any insight that measurably improves users' understanding of the model. Here, the user is very important because an explanation to you might be effective, but an explanation to someone who doesn't understand computer science or machine learning, it might be completely ineffective. So your audience matters a lot. And we want to improve people's understanding about the model. And this is itself very vague. What do we mean by understanding of the model, and how do we evaluate understanding of the model? So one particular benchmark or one particular metric that we introduce measures this understanding by simulatability. So let's say we have a group A where they receive some input output examples, and a group B which receives some input output explanation triples. So you can think of a black box as, let's say, an admission committee. So you have lots of applicants. Some of them are accepted by the committee, some of them are rejected by the committee. And you, by looking at some past examples, are trying to model what admission committee does. And at test time, you want to simulate what the committee will do. So let's say there is a aspirant who wants to know how likely is it that they might get into University of Utah. So what they might do is observe some past examples from the past iterations and try to understand whether they would get in or not. And now in the second case, when in a hypothetical case, when students also get explanations, like maybe those explanations are good explanations, like so and so faculty members are looking to expand in areas of interpretability and so and so, and your past background suits that, and hence you were accepted, and this is maybe a part of an explanation. So these explanations, if they are good faithful explanations of the process are likely going to help people simulate the admission committee better. So the degree by which the simulation accuracies improve with explanations versus without explanations is a quantitative indicator of how good are explanations. And this is just one view of understanding. And this is a very strong test for understanding. You might still understand parts of the model and not be able to simulate it.
I have a question.
Yeah.
So why do you think the committee 1 is not as good as the committee 2? Just they have to provide explanation. That doesn't mean like, why do you think like the committee 1, although they may have an explanation, they are not obliged to present it, doesn't mean like they are not doing the good job or like better job than the compared to
So
committee 2?
so in both the groups, both the control and the treatment, the committee is the same and their decisions are the same. In one case, those decisions are just communicated as accept, reject decisions.
Okay.
In the treatment, they also have some explanations. So the model or the committee is the same. And we're trying to explain the committee, and committee is in some sense just one example of a black box process.
Okay.
Yeah. So one other important aspect here is that during test time, when you are actually simulating decisions, you should not have explanations here. So if you have explanations during test time, that can almost certainly leak the decision label. So if there are even bad explanations or good explanations, let's say an explanation is just a simple generic explanation like, oh, we received far too many candidates and we regret to inform you that we could not accept you. This is an explanation. It's not a very good explanation because it's a generic explanation. Now, even that explanation will improve your simulatability because at test time, if you observe an explanation, that can encode the final label. So this testing phase has to be pure in the sense that you only observe the input and you have to simulate just by looking at the input. And this is one crucial difference between some other studies and the models we propose. And if there are explanations at test time, they can leak the label, and they do leak the label. Okay, so roughly this is basically our protocol. You have a teacher model that you're trying to explain, and you have input, output, and some sort of explanations from the teacher model. And you have a student model, which could be another black box model, by the way, who's trying to approximate the teacher model using input, output, and explanation triples. And if explanations are any good, then you would observe a higher simulation accuracy on test set compared to the case when you do not have explanations. So essentially the task that we are left with is defining what constitutes an explanation. And for the teacher model, the question to ask is how to generate that explanation. And for the student model, the question to ask is how do you incorporate that explanation during training?
So I've got a question. So, so you're using this explanation inside the space of the model. It sounds like it's going to get encoded in some automated process in some way, which is different from how I would think of an explanation as something you present to a human instead of into an algorithm or into a learning process, right? The explanation might be, well, here's the classifier I trained, right? That could be useful in learning, but to me or to someone kind of who doesn't understand how these models work, right? It doesn't tell them anything.
Yeah. So that's a very good question. So one potential explanation could be, look, here are all the weights of the model. And to a student, that's incredibly useful. And within one example, it can perfectly clone the teacher model and simulate it perfectly. So And for some simple models, let's say if a model is very simple, like a linear model with 2 or 3 variables, that even makes sense. Like you can say that, okay, the predicted house rent is just 2 times the number of bathrooms plus 3 times the area. And now people can simulate it. That's very simple. So sometimes weights of the model or parameters of the model might be good explanations. Sometimes they are bad explanations to people. So the first question, where what constitutes an explanation or what is the form of the explanation, is very important to ask here. You need to constrain the explanations that people can comprehend. So for text classification, for instance, we define explanations to be a subset of the input. So like subspans. Now you can present this to people, and a lot of people might find this useful. Like, I don't want to, let's say this is a long review, I don't want to go through the whole review, and I can understand that, yeah, the cinematography was outstanding and looks like maybe a good movie to watch. I could actually read the whole review, that's good too. But the point being that this is, you have to constrain explanations in a way that people might also understand. So a big part of our framework heavily relies on what form of explanations you use. And depending upon the form, you can only compare explanation methods who comply to that form. You really cannot compare explanation methods which have very different forms, because then the amount of information passed also will be very different. Yeah.
Are you? I have a question. Just to
Mhm.
follow up on the Jeff question. So, are you saying that the explanation you are used while you are doing the student model kind of thing are like, in a some way, part of the input only? It's not just something like an extra piece of information like the problem is explanation is always treated as an output, but here you are giving this as an input. But you are saying it's more like a constraint kind of thing,
So,
like.
so the explanation is an output for the teacher. It is
Hmm,
something that, let's say, teacher spits out, or
yes.
it could be, let's say, attention scores or gradients or whatever, for instance, people typically use.
Okay.
And they are output for the teacher model, but students consume that during training.
Okay.
Uh,
Okay.
and and we need to restrict explanations into a certain format, because we also want to evaluate explanations that people can understand. Some explanations are very effective if your models can actually understand it. But let's say if I gave you a huge BERT model and all the weights, very
Hmm.
likely you, me, Jeff, or anybody could not actually simulate all the weights in our head. So
Hmm.
that's not a useful explanation for us.
Okay.
Okay. Yeah. Mm. So for text classification, a lot of people have identified that subspans is a good way of identifying explanations. Uh, we also looked at a question answering task. So very recently, people got a lot of questions annotated with explanations, which highlight salient tokens in the question and their references in the passage. Like Michigan Stadium refers to the Michigan Stadium. Sorry, the University of Michigan Stadium refers to the Michigan Stadium, and the co-referring token it's, and so on. So this could be, let's say, the explanation format for QA tasks. One could define any type of explanation format, but a good exercise is to just also see if people might actually comprehend that. Okay, so this is basically just touching upon what could be plausible forms of explanations. Now, what could be plausible forms of explanations? People have already looked at multiple forms of explanations. Like, most popular explanation techniques that one might find in the literature might be, people want to look at attention scores, or people have looked at a lot of gradient based methods like norm of the representations, or gradient times the input, or even integrated gradients, where these gradients are integrated over a whole spectrum of a line, where they start from a reference image to the input image. Or there are other methods which are like, they try to approximate the decision boundary locally with the interpretable model, like what Lime does. Or basically it could be anything. You could bring your own explanation, and this framework allows you to evaluate the effectiveness of that explanation. So coming to how the student models could incorporate the explanation, this of course depends on what type of student models you use. So we used transformer based models, which are attention based models. So one method to incorporate explanations could be that you want to regularize some of the heads of your student to align with the mappings that you received as a part of the explanation. The other form of incorporating explanations could be multitask learning, where you are trying to jointly predict the output as well as the explanation. And if the two tasks are complementary, then one would hope that actually predicting explanations also helps you learn the task. So just to instantiate these two methods over the classification task. So let's say one thing you could do is you could regularize the attention from the CLS token, which actually makes the prediction, to whatever explanation tokens were highlighted by a certain technique. Or you could actually do a multitask learning where you're trying to predict zeros and ones are for tokens which participate in the explanation and zero otherwise. So you can model this as a, let's say, sequence tagging problem and use a CRF as well as a prediction model, and both tasks could share representations and so on. Same for QA, you can have attention heads from the question aligned to the references in the passage. And you could also do multitask learning here, where the first task is QA or classification in the previous case, and the second task is entity tagging, identifying which is salient entities and their references and so on. Okay, so these are just some methods that you could use to incorporate, and you could try different methods as well, and so on. So this is just trying to estimate how well can you use the information. Okay. So our first set of experiments try to understand if explanations that were generated by people are useful. So what we are trying to do is we are trying to suggest here that the teacher models are people. So people are giving us the output, as well as people are telling us this is the span that's important, or these are the important question entities. These are the same entities in the passage. So we are trying to learn from explanations from people. So here the teacher models are people, but the student models are BERT based models. And the red bars that you see are where model performance is captured without explanations. And the blue bars are where you capture model performance with explanations. And as you can see that attention regularization is immediately effective, whereas multitask learning takes about 900 or so examples to yield improvements. Because for multitask learning, you have to learn a new task, new set of parameters altogether for the CRF parameters. Whereas for attention regularization, it's immediately effective because you don't need to learn any new parameters, and you can think of explanations as some sort of inductive bias, and they're immediately helpful. So this is just establishing that human explanations.
Classification accuracy is just a question. Classification accuracy is on the test set without explanation or with explanation, like while testing.
So while testing, you only have the input without explanations.
Without explanations.
Because otherwise explanations could leak the output.
Yes. So this is the accuracy after that, like. But
yes,
the training
yes.
is done with explanation to incorporate.
So for blue bars, the training is done with explanations. For red bar, there were no explanations.
Yeah. Okay. Thanks.
Yeah. Awesome. So the same graph, but for the QA task, here the explanations for QA also come from people, and the answers also come from people. And here again, we notice that we have two methods to regularize attention. One is a simple method which just uniformly looks at all the tokens. And the other one is a very nuanced method which actually aligns the question tokens with the passage tokens. And they both are very effective. And here too, we see that multitask learning requires a lot more examples to learn the task. So multitask learning here is not very effective, but attention regularization is very effective. And here too, just like in classification, on the test examples, explanations are not available. And during training, for the blue and green bars, explanations are available during training. So these two experiments with people as teachers are only establishing that our methods to incorporate explanations are solid, in the sense that if you give me good explanations, they yield improvements in my system. And now what you could do is you could take a BERT model that you're trying to explain, and let's say 5, 6, 10 explanation techniques that you are trying to evaluate, and see how well can you build students to simulate your BERT model. So here, the teacher model is also a BERT model, and a student model is also a different BERT model. And you're trying to see how different explanations help the students simulate. And this is in some way like a quantitative way to evaluate different explanations. And here we notice that attention and integrated gradients are one of the most effective techniques, where attention is the most effective technique. And we found out that saliency-based methods like gradient norm and gradient times input are not very effective. Lime is also not very effective compared to the no explanations control. So this is in some way like first of the works that could actually quantitatively rate explanations on a large data set. And one another interesting thing to note here is that both the methods to incorporate explanations, that is attention regularization and multitask learning, they both are very consistent with the trends that we observe. So for both these incorporation techniques, we find attention is the best explanation, integrated gradients is the second best explanation, and so on. And here too, we notice that for 500 and 1000 examples for multitask learning, the differences are very, very small, because it is very hard for a new model, which is CRF, to learn a sequence tagging task with very few examples. Okay, so this is like the takeaway from the slide is that you could actually rate explanations. This is for the QA task where the explanations and the outputs come from a SpanBERT model, which is a model developed in a recent work. And here we notice that the explanations are actually very good. So the red bar is basically without explanations, and blue and green bar are with explanations at training time. And these explanations actually help. And these explanations help a lot, especially in low resources, because that information is very valuable to simulate if you have very few data points. If you have lots and lots and lots of data points, then the additional utility of explanations is diminished. And with 16,000 examples, you see almost no benefit. And just input output is enough to approximate the teacher model. Okay. So just to conclude this part of the talk, we are essentially trying to make a case that you can formalize the value of explanations through this student-teacher framework, where explanations are treated as a communication from a teacher to a student, and the value is assessed by how well they help in simulating the teacher on unseen examples when explanations are not available. So any questions so far before we move on to the next part of the talk?
Yeah, sorry.
Yeah.
Yeah. So I want to ask, like, is it something like what you are trying to do is like you want to look at the easiness of explanation to mimic it? Like if the teacher explanations are easier enough for the model to incorporate, then the student model will learn it well. Is that
so what we are,
which you want to compare when you say like you can rank explanations?
So we are essentially saying that like the adjective I would rather use here is informative. So whatever explanations are informative, they tend to help the student models more. So if your explanations tell more about the black box process, then that's good. If they do not indicate about the process, then that's not good. And that's why maybe they will be ranked lower in the metric.
But is it also dependent on the learning ability of the final student model to incorporate those explanations? Because maybe it's possible that, for example, in your same case, you said that the meta uh, reinforcement learning thing is harder kind of thing, so that's why it was not able to incorporate that explanation well. But maybe that explanations are equally informative, but they are just harder to for any model to incorporate kind of thing in learning
Right.
or something.
So there is, so what I'm, so maybe there exists some student models and some techniques to incorporate explanations that can make use of even, let's say, explanations that we didn't find helpful. So I'm not trying to suggest that those explanations are not useful, but this metric suggests that given a student model and given a technique to incorporate it, these explanations are useful. And as I said initially in the talk, the explanations for whom matter a lot. So your audience matters a lot. What is your student model is important to capture. So in our paper, we experiment with a lot of student models, and the results are consistent across different student models. And as any human educator might appreciate that, like, one explanation might not work for everybody. So depending upon the background of the student, you might have to tailor your explanation accordingly. So ideally, the metric could be extended in a way where you average the benefits of explanations across a distribution of students. So right now, all the results that I show here are for one particular student. The paper also looks at multiple other students, and the results are consistent. But the ideal case to avoid such problems might be to consider more students.
Okay. uh, by student here you mean a model, no?
Yeah. Actually, the
Okay.
student in principle could be a human being,
Yeah, I was
but
thinking that why, since you have made teacher also once a human, to see how like golden explanation should look like, which can basically be used by a student model to me. It's also look like we can also think of how, like, given an explanation by either a model, like whether teacher is a model or a
right.
human, how well a human will comprehend it and incorporate in his decision process.
Yeah. So there have been some studies which have tried to understand the simulatability aspect with students, with real students. And the observations there were that with they trained students for about 1632 examples. So that is very few examples. And the problem they observed were more logistical constraints. Like it's very hard to recruit people
Yeah.
to train themselves for 8,000 examples. Like I particularly wouldn't participate in any such study.
Yeah, it makes
so,
sense.
so, and sometimes like you might be able to tease apart differences only when you train students for a certain number of examples. So it is important to automate this because typically, like the study that you want to do with people is going to be very, very hard logistically.
I was thinking of other way where if you can train the student not by explanation, which is somewhat like examples, but train
Mhm.
them by rules, like
Mhm.
similar to a model kind of thing. Like you get people admitted who have, for example, GPA above this, who have this, who have this. These are the exception, like 2 pages of thing. And now you give explanations, and then the humans or the student model, which is a human, evaluate based on those rules how much
Mhm.
these explanation fits in
Yeah,
that
yeah.
category.
So
Maybe
definitely,
that's is a more feasible approach than like obviously like 100 800 examples
yeah,
kind of
yeah.
thing, but still it's a tough task for any human
Yeah, it's
basically.
a tough task, and but the framework here is very general. You can potentially swap out student models with actual students.
Okay.
So can I ask a question as well, or
Yeah. Please,
maybe
please.
also pose a different explanation of this to your thoughts on this. So one way of thinking about this with the when you're highlighting these examples or these effectively these exemplars, which are the things which the model is using the most. It seems like kind of like what you're doing is this only works when you have small data. And what we've started to learn about these very big models is they're, to some extent, interpolating through what the data is. And what you're giving when you don't have enough data to build a model where you're interpolating is you're telling it how to weight the data sets that you do have. Say, these are the ones which are really important, and that will help you kind of understand better the distribution of the data that you don't have. Is that kind of a fair way of thinking about this?
So let's say if a student learner is a different learner which can weigh different data points differently, then an explanation that suggests or provides quantification about weights of these points, like students might learn much faster and better with that. So yes, like depending upon your student model, one could say that they are benefiting because they are learning about which data points are more important. Like if the student learner is, let's say, an SVM, if you tell about the support points, it's going to help a lot, and so on. So depending upon the student learner, different explanations might actually be better. And which is actually, I think, a reasonable assumption because that's what also happens in practice. Yeah.
So great, thanks.
Yeah, thanks. So quickly moving on to the next part of the talk. So this part of the talk looks at evidence. Evidence is slightly different from explanations, and the way we define evidence is that you want to identify input spans that can enable stakeholders to validate the correctness of outcomes. So we don't particularly care if the model was right for the right reason or the wrong reason. What we want to supply here is justification or parts of the input that someone can quickly look and say that, yes, this is right. And if it does not look right, then they automatically have to review the whole thing. I'll give you a few examples. So let's say this is the movie review. I can read the whole movie review and make a decision whether I want to go watch the movie or not. Or I can just see this. And this movie review was classified as positive, and looking at the highlighted spans in this particular movie review, it looks like that this was actually a positive movie where the cinematography was outstanding, the message was artistically interesting, and so on. So I don't need to read the whole review because the evidence is compelling enough. If the evidence is not good, I'll have to go back and read the whole thing. And this happens a lot in other things as well. So one application here is, let's say this particular tweet was identified to be violating the principles and about glorifying violence. And let's say if I could highlight that, okay, this is the line that actually glorifies violence, people might be able to verify it quickly. Same could be said about any scientific claims, like this claim, vaccines cause autism. Let's say it's disputed and you could pick out relevance from a scientific journal or an established source of authority that provides evidence for that. And people can look at that and then say that, yes, this claim is disputed. So evidence, contrary to explanations, is more of a property of the task rather than the model. And evidence basically enables people to quickly verify predictions, whereas explanations are more meant to elucidate the reasons behind predictions. And evidence is, of course, simpler to evaluate because you can compare it to ground truth evidence. You can compute overlap and so on. So one example here might be that, like, for the sentiment task, let's say the review is a horror movie that lacks cohesion. It might so happen that a lot of the data was such that horror was so much negatively correlated. It was correlated to the negative class. And people have found out that in IMDb particularly, the word horror is very correlated to the negative class. So maybe this looks like an explanation, Whereas a good evidence for this might be that the movie actually lacks cohesion. And we want to, so one important point to note is that if we do not have any supervision about what is evidence, what we can only give out is just correlations. So if we have only X and Y's, we will not be able to tell that horror, which is simply correlated to the label, but actually does not cause the label, is not an evidence. So we need some sort of supervision that actually points us to evidence. Otherwise, we cannot make the distinction, because otherwise we will just land up in the land where we are computing correlations.
I have a question. Doesn't like evidence leads to explanation? Like if I want to reason about some label, I basically look at the evidence and then I say, okay, because of this, this is the reason I labeled it that. And maybe
Yeah. So
maybe I don't
go on.
use all the evidence, or I just use some bias evidence in the evidence. For example, in this case, you say the explanation is horror, but the evidence can be both lack of cohesion and horror kind of thing, or some maybe only lack of cohesion.
Yeah. So basically, for people who are very, let's say, maybe diligent about the task, explanations and evidence might look the same thing, because the explanations they give are based out of evidence and maybe even some reasoning on the top of evidence. But for data sets and for models, they might actually be different things, because like what you want for evidence is like verifiable portions of the text, but explanations will only be correlations or what model has picked up. Does it make sense? For people, these two are very similar things.
Yeah, for people, I feel like the evidence is the one which you look for and then you basically explain. So if, for example, a movie sentiment has some positive aspect as well as some negative aspect, and then I give my rating as, for example, 2, then I say because I value these negative aspect more, which is bad in the movie, and that's why I give it a negative rating.
Yeah. That makes sense. Yeah.
Okay.
So explanations, like for people, the process is slightly different in the sense that we might highlight evidence and then on top of it, we might reason over the final label.
Yes.
Which makes complete sense. But here, the differences we are looking at are for models, and a lot of these deep learning models are just associative machines. So the associations they capture are in some way explained through explanations, whereas evidence is more like a property of the task.
Interesting.
Yeah.
So models, somewhat it's in short as like model may not be using evidence for explanation, and we need somehow to model somewhat also rely on evidence for explanation or something.
Yeah. So you could build models that rely on evidence, but here we are trying to give evidence to people so that they can quickly review these documents. So one very practical use case that we have is we have, for instance, a Highmark, which is a huge insurance company. They want to, for instance, bill people. And to be able to bill people, they need to identify whether the patients are treated, educated, assessed, and so on. So they have all these conditions and they have classifiers that actually do some predictions, but they're not completely accurate. So it's not that all the classifiers are so accurate that you don't need a human in the loop. But despite those, you need to in some way surface evidence that, okay, this is why, like this is the evidence for the positive class, or this is the evidence this is the evidence for saying that the patient was educated. And if that evidence looks good, then the people can just say that, okay, yeah, this looks good. I don't need to go through the entire clinical note to make a call. Yeah.
So can I, so I'm worried. So I've been looking at some issues in fairness and bias. And I'm so concerned that the shift from an explanation to some form of evidence is moving from some biased decision to some sort of post hoc rationalization of this that hides where the bias is coming from, but still making the same decision. So is there something you can say about this to either say, yeah, maybe this is a problem, or to sort of allay my concerns about this issue?
Yeah. So we are specifically looking at problems where no classification system is good enough to actually be deployed on its own. So one of the tasks that we study is propaganda detection. And the task itself is so complex that no classification system is actually very good. So we need humans in the loop, and there are people in the loop. And now the question more so is that, can we save time for people so that they don't have to go through the whole document or the whole news article to validate propaganda? And if, let's say, we have detected propaganda, can we just point to some subsections in the article that we think propaganda is located in? So we are, like, one might say that we are trying to rationalize biased decisions through evidence that looks good, which could happen. But the point here is that we are trying to surface out evidence that people can look out and say that, yes, this is a case of propaganda, or this is a case of misinformation, and this should be taken down.
But is it a problem that an automated machine, has limited the information they're seeing? So once a potential decision has been made in an automated way to get them past the first, the flagging stage, they say, here, we hope this will convince you. When if they had looked at the full data set, they would have gotten context of it and realized it was a joke or or something else, or it was part of a cultural kind of aspect which justified this sort of things, but they've lost that context.
Yeah. So that is a very good point. So, like, in isolation, something might look like violating a certain principle, but it might just be sarcastic if you look at the whole context. So those are good cases, and those are some things which would be a problem for our system, because if the evidence looks compelling, somebody might move on. However, having said that, depending upon the kind of the domain and data, people might be more, they might have a higher threshold on what is compelling. So they might want to tune that themselves, that, okay, we have witnessed in the past that when people say this, that is not immediately propaganda, and in certain contexts, that's okay to say.
Yeah, it's great. Yeah, and I didn't mean to criticize this work. This is an incredibly hard challenge. So
yeah. I completely agree with you. Like, in certain contexts, it could actually be misleading, where we're trying to suggest that this is compelling evidence, but if you look at the whole context, it might make sense. So that is definitely like not something that our system would handle well as of now. Yeah. Okay. So moving on, like, the approach that we take here is basically we are jointly trying to model both the label and the evidence. And evidence is just a binary mask which points out which token is a part of evidence versus which is not. And there are two ways to factorize it. One is basically that you extract first and then you predict it. So this is what a lot of, like, interpretability literature does. They will extract and localize first, and using that they will predict. The other thing that you can do is you can predict first and then extract. And this is better in some ways, because now this is more amenable to the case when you have only few rationales or few evidence. So remember, we are looking at a setting which is only semi-supervised. We don't have the bandwidth to get a lot of examples annotated for evidence, but we definitely need a few. So the setting we consider here is a semi-supervised setting where we have 5% actual annotated evidence. So we have strong supervision for a few examples and a lot of weak document level supervision, because we have input and output as well. And that is some supervision. So this is more suited for like weak supervision and actually semi-supervision. And the other good part about this is that now you can actually condition your evidence on the prediction, and that might be helpful. And I'll give you a few examples later. So now this particular term could be any classifier, your favorite classifier, and this could be, let's say, a linear chain CRF. And now you can also be very creative in what your emission and transmission features are. And like one way to think about this is that you can actually use the features from the classifier, also the features that you use for emission. So basically you will be able to like mark words that were also important for classification. So in some way they work in sync. So like these are some baseline approaches for evidence extraction. And like some of these are just like top K from attention or supervised attention. And these are some methods from past literature which do something similar. And these are our methods. So this is just extract only baseline, where you simply use 5% of your data and just do extraction. So you train a BERT based CRF model with just a sequence tagging. And this is classify and extract. So in some way you are now doing multitask, where one task is classification and extraction and the parameters are shared. So you see a lot of boost. And now if you condition on the predicted label, you see some more boost, because now the evidence can be tailored to the predicted class. And you see more boost if instead of the predicted label, you give the oracle label, because predicted label and oracle label might differ for some examples and it might be better. So this is for sentiment classification for movie reviews. We have a similar set of results for propaganda detection, where our methods are better here too. And here too, we notice that actually conditioning on the label helps more so on the oracle labels, because classification labels are not very good here. And the classification accuracy is only about 70%, because it's a very hard task to detect propaganda or not. And this graph very quickly tells us how prediction also benefits extraction. So the white line just does extraction with increasing data, and the green line above it does prediction as well as extraction. So you are in some way using a lot of document level labels to better do extraction. And as I said, you can like say that, okay, this movie review was classified as negative, and this is your explanation, or this is your evidence for negative that the model picked up. But now you can manually flip that negative label to a positive label, and this model can actually even give you evidence for the positive label. So especially useful when there are multiple classes that could happen. Let's say if you have a mixed review like this, you might want to see both evidence for positive as well as negative. And it can point you to evidence, and all you need to do is just flip that Y label, because it's conditioned on the label, and depending upon the label, it can change what is evidence. Yeah, so this is pretty much all I had, and happy to take questions.
Thanks, Danish. Wonderful talk.
Yeah, so thank you. So any questions from the audience? I know so Vivek and I have been asking a bunch of questions. Oh, and here's this overdue. So applause. You can hear that.
Yeah, that's nice.
Yeah. So yeah. So anyone else from the audience have any questions? So thanks. So I have one other comment, I guess. So I'd like to. So I don't know if you've heard of this area that's I guess come out of the algorithms community. So called like core sets. These have been trickled into machine learning, like for k-means clusterings and stuff like this, where you can find a small subset of data that you can do that quickly, and then you can train just on the subset and get hopefully high accuracy. Do you view this idea of these sort of explanations you have as pulling out these subsets of the data which are providing intuition of what's going on? Are those kind of in spirit? Do you think this is similar to the idea of a core set, or is it somehow different in that it's meant to explain a particular explanation, not a subset which is useful for doing the full training on the
so
the data?
So the evidence is useful for a stakeholder to validate. So it might be useful also for training, and in fact it might happen that models trained on evidence are better or more robust, but that's not something we have particularly studied in this work. And like the closest analog I can give might be in computer vision, like where you try to identify boxes or bounded boxes for objects and certain classes and so on. So this is in some way a localization problem. Yeah.
So thanks.
Yeah.
So are there any other questions?
I have a question. So have you also evaluated these with like, for example, if I give this example to a human and with both label negative and positive and ask them for the evidence, do they do similar, and how well they do compared to a model?
Right. So these all evaluation metrics that I showed are overlap with human evidence. So the 45 overlap means roughly half of what we give is the same as what people identified.
Oh, this is human overlap.
This is overlap with humans. And for evidence, you want to give evidence that people found useful. So evaluation for evidence extraction is very straightforward. All you do is you compare it with human evidence.
And also, like, I have a concern, like, because this evidence is coming from the model, so don't you like it? Why don't the model like see what biases it find to get the answers rather than like actually providing that? Or this is the way of evaluating either the model is doing something. Do you find like maybe model is using biases and then giving like very bad
explanations are a better candidate to spot biases. Evidence is more like a property of the task where you are just trying to localize what you think is valid enough for the label. So if you want to, let's say, identify biases or understand fairness constraints and so on, like the candidate to look for are maybe explanations, not evidence. But here too, the models actually, so one last thing I want to say is that since models benefit a lot from predicted labels, and like as you can see, prediction plus extraction is a lot better than just extraction. So in some way, the prediction model is being used for extraction. So there might be, you might be able to spot some biases, but if that is your sole goal, then you should not use this.
Okay. So my point is where it could be useful. You are saying if you want to, like, for example, deploy in a company and there you basically use, because the thing is like maybe the prediction is using some other explanation to get to the right answer, which may be biased, but it's providing the right evidence. It might possible that it's now able to predict the right evidence, but it's somehow using different thing to get to the label initially, because now you are predicting the evidence later after once you get the label.
Definitely. So I'm not making any claims about faithfulness of the evidence with respect to the model. And I'm saying like the practical utility arises when you want to quickly verify outcomes. So sometimes, like in the medical domain, like the example we have and the problem we are actually working with for one of the organizations is where certain conditions are to be met for the clinical note to be built. And if you can locate where exactly that information is provided, and if people can quickly verify that, that's good. So for some tasks, all you require is whether that information is present or not. And you want to
Okay.
quickly validate that.
Okay, there I think it could be helpful, but checking whether the model is doing the right thing, this might not be
Yeah,
like
yeah. So
trustable kind of thing,
yeah,
because
yeah. This is not meant to look at model internals or understand the model.
yes,
This is for the convenience of people who are otherwise going to look at the whole thing.
yes, okay,
Yeah,
I got the point. Okay, yeah, that's
yeah,
was a major, I think, the difference between explanation versus evidence.
yeah. So the task here is just to enable stakeholders to
Interesting.
quickly verify the outcome.
That's an interesting new task. Yeah, interesting. Cool. Yeah.
Yeah, so great. So thanks a lot for the great talk. This was very, very interesting, and I think I have a kind of broader view of kind of this area of kind of understanding our explanations in these models. So great. So thanks a lot. So thank the speaker again.
Thanks.
And so if this was the last talk of the semester, thanks everyone for coming as well, and we'll and so either we'll see you next week or we'll see you next semester.
Yeah.
Okay. Yeah, and thanks
everyone.
everyone, and thanks Jeff and Vivek for hosting and the questions.
Thank you.
Yeah, of course.
Bye.